program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
the alchemists of the Middle Ages tried to turn base metal into gold. Today, industrial chemists routinely turn oil and natural gas into thousands of synthetic polymers, which redefine the way we live. We have learned how to create materials harder than steel, softer than silk, and far less expensive than either. What is the secret? How have we created the age of polymers?
Stone Age, Bronze Age, Iron Age. The ages of man are defined by the materials that we use. What age are we living in today? This is the age of large factory-made synthetic molecules called polymers. Polymers are all around us, and they've replaced many of the materials that we normally use. Are polymers, in fact, something new? No, they're not. Cotton, wool, wax have been with us since the beginning of civilization, and these too are large molecules. We call them biopolymers. And we certainly haven't been replaced. We are largely macromolecules and water. What is so special about polymers, natural or synthetic? And how have we learned to make these? Because after all, the simple building blocks that nature provides us are small molecules, and these are quite complicated larger ones. It is only in this century that we have learned to tailor and control the properties of the molecules that we make.
In our daily lives, we are surrounded by materials that are totally new. Synthetic polymers clothe us, shelter us, protect our food, protect our bodies. We walk on polymers, we skate on polymers, we play football on polymers. The colors and sounds of everyday life are created and reproduced on synthetic polymers. Yesterday, the word plastic meant cheap and inferior. Tomorrow, plastic may replace our bodily organs as they begin to wear out. How does modern chemistry create all these new materials and products? How can we get so much diversity from a common starting point? We are about to show you how thousands of small molecules are combined into giant macromolecules called polymers. You will see how one small molecule, ethylene, can become a building block for so many different polymers and products. Yet they, and ethylene, all have a common origin in crude oil or natural gas. Every day, the world consumes another 5 billion liters of petroleum. Nations rise to prosperity or slide into poverty, depending on fluctuations in the price of a barrel of crude oil. But without processing, crude oil straight from the ground is practically useless. Crude oil comes to the refinery as a complex mixture of gaseous, liquid, and solid hydrocarbons. The first step in refining the raw crude is called fractional distillation, and it takes place in these huge towers. Hot crude oil is fed in near the bottom of the tower, where it is heated again with steam. The column is cool at the top. Lighter hydrocarbons, those with fewer carbon atoms, boil at a lower temperature and rise to the top of the tower as gases. Heavier hydrocarbons, those with more carbon atoms, flow toward the bottom of the tower as liquids and solids. Nothing is wasted. At the very top of the tower are the gases: methane, ethane, propane, butane. Next comes gasoline and many important petrochemicals. Below that is the kerosene fraction for jet fuel. Then there is diesel oil, and at the bottom, lubricants and asphalt. At the end of this process, 1 barrel of crude oil leaves the refinery as a variety of important substances. But are these substances all equally useful? How do we get more of what we need the most? Crude oil does not yield enough gasoline or even ethylene through fractional distillation to meet our demands. Fortunately, both the heavier and lighter fractions can be subjected to further treatment known as cracking. These huge chambers are catalytic cracking towers. Here, the heavier hydrocarbons are subjected to heat, pressure, and the action of a catalyst. The heavy molecules crack into fragments of lower molecular weight, producing more hydrocarbons in the gasoline range. By adjusting the quantity of material that is handled in each of these processes, the refinery can produce the commodities that society needs the most. That's how we get more ethylene, a fundamental molecular building block of synthetic polymer chemistry. This is the molecular geometry of ethylene: 2 carbon atoms and 4 hydrogens. The ability of ethylene to form polymers comes from the double bond which joins the carbon atoms. Ethylene is a monomer. Standing by itself, it doesn't polymerize until we add an initiator, such as this organic peroxide. The bond between the oxygen atoms splits apart to form free radicals, reactive particles with unpaired electrons. The free radical quickly combines with an ethylene molecule. The product is also a free radical. It too reacts with an ethylene molecule. This is repeated many times and the chain grows. This sequence is called a free radical chain reaction. Eventually, we must stop the process or the polymer chain will be too long. The reaction ends when 2 chains link up. Imagine a freight train being assembled 1 boxcar at a time. Each car rolls down the hill and clamps onto the car ahead of it. Then along comes another car, and so it goes. Many cars become 1 train. Today, polyethylene is the world's most popular synthetic polymer. We manufacture 6 billion kilograms of it a year. It's a clear, stretchy food wrap, or an impenetrable protective garment. It's a bowling pin, a fuel tank, a skating rink. Polyethylene has many different uses and many different properties. Series demonstrator, Dr. Donald Showalter.
Let's examine some of the material around us here. All of this stuff is polyethylene. Some of it bounces, some of it breaks, some of it tears easily, some of it doesn't. Why do these common objects have such different properties? There are many different kinds of polyethylene. I'm going to show you 3. Let's take this stuff. You may call it sandwich wrap. I call it low-density polyethylene. It's very flexible. How about this bottle? I can crush it. I could probably even tear it, but it would take some hard work. It's made from high-density polyethylene. The bottle might be tough, but the cap is even tougher. It's made from cross-linked polyethylene. How can one substance, one polymer, have so many different properties and lend itself to so many different uses? The diversity that we find in all of these products is a reflection of the diversity we find in the structure of the polymer chains. Let's see how that works.
If we heat ethylene in the presence of certain catalysts, we get a polymer with very long, straight chains. Because the chains have few or no branches, they clump together. Imagine a rope. Many strands together are stronger than a single strand alone. Polyethylene made this way is fairly strong. How strong is this high-density polyethylene? The manufacturers have a variety of ways to find out. The polymer can be tested for tensile strength or impact strength. Here's a test for column crush strength. And these machines test flex strength. This is a test for environmental stress crack resistance. Polymer chains that are even tighter and straighter make for even stronger polyethylene, giving us such materials as very high and ultra-high density polyethylene. But what about this polyethylene? It's low-density polyethylene, much shorter chains and many branches in each chain. Because of the branches, the chains don't pack together well. Instead of coiled rope, we now have something that looks like tree limbs. Low-density polyethylene is more flexible than its high-density cousin, but it's also weaker. It's fine for transporting goldfish or wrapping fresh produce at the food market. Low-density polyethylene feels greasy. It stretches, grows thinner, then pulls apart. Let's see that in the molecular world. Under tension, the chains slide, then separate easily. Now, what would happen if we add a catalyst that caused these branches to hook up with other polymer chains? This is called cross-linking, and this third example of polyethylene has a web-like structure. What properties might we expect now? Cross-linked polyethylene acts like a hammock. It's very difficult to tear. Plastic ice is made with cross-linked polyethylene. Soft drink bottle caps are made from cross-linked polyethylene. The plastic bottles themselves are made from another polymer, polyethylene terephthalate, or PET, and represent the solution to a formidable challenge: how to create an inexpensive container able to withstand a gas pressure of several atmospheres. The inventor of the polyethylene terephthalate soft drink bottle is Nathaniel Wyeth, who comes from the internationally famous family of artists. His brother, Andrew Wyeth, expresses his creativity on canvas. But Nat Wyeth expresses his through chemical engineering.
I got to thinking about the work that Wallace Carruthers did for DuPont way back in the days when nylon was born, where he found that if you took a thread of nylon, when it was cold, that is below the melt point, and stretched it, that it would orient itself. That is, the molecules of the polymer would align themselves. This is what you're doing to the molecules when you orient them. You're lining them up so they can give you the most strength. They're all pulling in the direction you want them to pull in.
But the bottles kept splitting. Wyeth estimates that he made 10,000 tries and 10,000 failures before he came to make a simple observation.
Well, Well, then I realized what we've got to do now is to align these molecules in the sidewall of the bottle, not only in one direction, but in two directions. So I thought I'd play a trick on this mold, on this problem. I took two pieces of polyethylene and turned one of them 90 degrees with the other. So then I had one that would split in this direction, one that would split in that direction. Well, one piece reinforced the other. As soon as I did that, I could blow bottles. That seems almost dirt simple. But as I've often said, quoting Einstein, the biggest part of a problem and the easiest way to solving a problem is to understand it. Have the problem in a form that you understand what's going on. And what I was doing here was learning about what was going on. Once I knew, it's just simple to solve.
Someday, billions of plastic bottles may grow into mountains of garbage. Some bottles can be recycled. Others can be burned as an energy source. But creative minds may find even better solutions to the problem.
One of my dreams is that we're going to be able to melt these bottles, the return bottles, melt them down, mix them with reinforcing fibers, and make car bodies out of them. And that when the car has served its purpose, rather than put it on a junk pile, melt the car down and make bottles out of it.
Creative chemistry. We've seen it in action. We've seen how it's possible to make one substance, such as polyethylene, that has a wide variety of properties. But the easiest way to make new polymers is to alter the chemical composition of the beginning monomer. Such changes will radically affect a polymer's characteristics. Let's see what happens when we begin to make simple changes in an ethylene molecule.
Here's ethylene, just showing the molecular geometry. Let's remove one of the hydrogen atoms and substitute a benzene ring. We have produced a new monomer. This is styrene, a large and bulky molecule compared to ethylene. The polymer of styrene is polystyrene. The benzene rings stick out at random to the left and right. What properties can we expect this material to have in the observable world?
Think of this cup. It's polystyrene. It's clear and it's lightweight. But so is this cup, and it's polyethylene. What's the difference? The polyethylene chains are more flexible, so the cup is easily bent. The polystyrene cup shatters. It's brittle because the polystyrene chains are more rigid.
Polystyrene makes excellent insulation against heat or cold. Up to 90% of this material is air. It's bulky, but it's lightweight and easy to work with. Here's ethylene again. This time we will replace one of the hydrogen atoms with a cyanide group. This is the monomer acrylonitrile. The polymer is polyacrylonitrile, a tough fiber which is woven into clothing and carpets.
This is polyacrylonitrile. It's much too tough to tear. What's going on here? Why should the addition of a cyanide group make this material so tough?
The difference is a result of polarity. The acrylonitrile is more polar than the ethylene unit, so the polymer chains containing cyanide groups are attracted to one another more than the chains with just hydrogen atoms. That's why we walk on tough polyacrylonitrile and wrap sandwiches with flexible polyethylene. Acetylene is a highly combustible gas used in cutting torches. Polyacetylene is a solid with some interesting properties. When we remove two hydrogen atoms from ethylene, we get acetylene, which polymerizes to polyacetylene. When polyacetylene is mixed with certain metal compounds, it conducts electricity. Notice the alternating double bonds. This system of alternating double bonds allows electrons to move freely through the structure, just as electrons move freely through the metal in a piece of wire. This piece of polyacetylene is completing an electric circuit. When the polymer is dosed with an iodine solution, the circuit is completed and the fan turns. Researchers hope that polyacetylene may become the battery material of the future. Perhaps someday a polyacetylene battery, molded in the shape of a door panel, will provide the power for tomorrow's electric car. The United States consumes more plastics every year than steel, copper, and aluminum combined. Some of the most dramatic applications of polymer research can be found in automobiles. It's not only automobiles that benefit from the revolution in plastics. Commercial jet airplanes save millions of dollars per year in fuel costs by using polymers. And space exploration is increasingly dependent on synthetic polymers.
5, 4, 3, 2, 1. We have ignition and liftoff. And the shuttle has cleared the tower.
For some thoughts on the direction of polymer research in the 21st century, we went to Howard Simmons, head of research for the DuPont Corporation.
Many places where we use metals today, particularly in structural applications, these will be taken over by polymers in the future. Some of the more exotic things are in the area of medicine, where big markets are forecast in, for example, prosthetics. Right now, today, most artificial bones, joints, ligaments, even arteries are all made of sophisticated man-made polymers. I just saw in recent market estimates saying that by the 1990s this would be over a $2 billion business. A prime reason for this is that polymers allow almost infinite variation in structure and hence almost infinite variation in their properties, whereas we now know almost all there is to know about metals and glasses. Obviously not everything, but almost. There are almost an infinite variety of polymers that we can conceive so that we can fine-tune their structures and fine-tune their properties given enough time.
To review, polymer science has come a long way in the 20th century. 100 years ago, we had not yet created our first synthetic polymer. Today, we routinely use polymers in medicine, in construction, in transportation. Polymer science begins with breaking crude oil into its component parts through the two processes, fractional distillation and cracking. We make a polymer by stringing together thousands of small molecules, such as the ethylene molecule. This is polymerization. We have shown it taking place in a free radical chain reaction. The product is the versatile polymer polyethylene, the most common of the synthetic polymers. These polymers have a wide range of different properties: hard or soft, flexible or brittle, insulators or conductors. Depending on the size, structure, and chemical composition of the polymer chains. Polymer chemists continue to alter the structure of molecules or to change the basic building blocks or monomers to create totally new materials which imitate, even improve on natural substances.
Before we ever began to play in a laboratory, nature made abundant use of polymers in and around us. Why polymers? Well, molecules by themselves have certain properties, but when we string them into chains, when we arrange them into beautiful 2- or 3-dimensional frameworks, these properties change. The polymers gain strength. Nature made use of polymers because they suit it. They suit us. We do well to follow nature's example here in the laboratory. But is there something inherently different about the synthetic polymers that sets them apart from the natural ones? Well, of course there are differences. The differences are there among the synthetic ones. Nylon is different from rayon. They are there among the natural ones. Cotton is different from wool. But more interesting than the differences between the natural and the synthetic ones are the similarities which, in fact, emerge from the molecular level. To see a spider spin her web is hypnotic. It draws us in. It's beautiful. It's also interesting to see how she does it, how her silk glands and spinnerets work. And to me, it is fascinating to go in at the molecular level and to find out how her enzymes make that silk. It is no less beautiful to see a chemist come up with an entirely new process for making polyethylene, and then to watch her implement it at the level of thousands of kilograms an hour pouring out of a factory. The human mind has come up with an ingenious solution to a difficult problem. Human hands, guiding tools, have put it into practice. Surely this too is natural and beautiful.
Funding for this program was provided by the Annenberg CPB project.